So we finished off last semester talking about inverses. And there are a few types of equations which we didn't really look at the inverses, and one of those is the exponential equation. So I want you to just take a moment, think back when we talked about our parent functions. There are really two types of exponential equations. You've got exponential growth, which kind of looks like this, and levels off at y equals 0. And then you have exponential decay, which does the exact same thing, but sideways. So it comes down really quick and then levels off as you go to the right. These are both exponential graphs. There you are. We haven't looked at the inverses of these. Well, that's what this is meant to do. Introduce us to what the inverse of an exponential is. So you'll notice here, 553, that means that this is coming from your textbook. So if you ever want to follow along again, it is right in your text. 553 means unit 5, and it's the 53rd entry. This is at the start of section 5.2.1. Okay, first off, make a table. We're going to use y equals 3 to the x as an example and make a table of the inverse of what that would be. Here's the easiest way to do that. Let's start by making a table just of what y equals 3 to the x would look like. So 3 to the power of x. And we're going to use -2, -1, 0, 1, and 2. We're going to use 5 different exponents. This will also serve as a refresher on how to work with these different types of exponents. So let's start with the easier bit, the whole number positive exponents. So 3, for example, to the power of 2. That just means 3 times 3. I hope we can agree that that's going to give you a 9. 3 to the power of 1 is just 3 times itself 1 time, so just 1, 3. There you go. Now here's your refresher on how to use these exponents. 3 to the power of 0. Anything to the power of 0 is going to give you a 1. The only exception is 0 to the 0, and that doesn't come up very often. Now with negative exponents, this can be confusing for folks, so here's your refresher. Negative exponents just give you fractions. That's all they do. So 3 to the negative first is just the reciprocal of 3 to the positive first. So instead of a 3, it's going to be a 1 over 3, 1/3. 3 to the negative second is not going to be 9, but rather 1 over 9. Notice that even though the exponent is negative, the result is still positive. All the results are going to be positive. 3 to any power, whether it's a negative or a positive, is going to give us a positive result in the end. So this is the original function, y equals 3 to the x. Now let's take a look at the inverse. I want to label these columns here. These were our x's, and then these were our outputs, the y's. When you're talking about inverses, I hope you remember this because this was really the big idea. You just take the x's and y's and you switch them. So for the inverse, when we're looking at our inputs, it's going to be this list of y numbers. So the 1/9, the 1/3, the 1, the 3, and the 9. And the outputs become what the original x's were. The -2, the -1, the 0, the 1, and the 2. So there we go. That is a table of what the inverse function of y equals 3 to the x looks like. Next up, sketch a graph of the inverse. Okay, so I want to do this in 2 ways. First, let's make a table. Just putting in the numbers that we had. So we had 1/9 as an input on the inverse, giving us -2 as an output. We had 1/3 as an input, giving -1 as an output. 1 in was 0 out. 3 in was 1 out. And 9 in was 2 out. Now these points on their own aren't enough to give us a sense of what the overall graph looks like, but you can see a trend, right? It looks like we got a graph that's going to have some curviness to it, and it's going to go up, but it looks like it goes up kind of quick and then slows down. So let's now make a more complete graph. So our original function, don't forget, was y equals 3 to the power of x. So this is the original function that we started with. For the inverse, type the exact same equation, but remember in an inverse, you just switch the x and the y. What you should see is a graph that goes exactly through those points that we plotted, because the points are just examples of ordered pairs that are from this graph. Here now, in mine, it's in blue, is what the inverse function looks like. So some things to notice. I'm going to zoom out a little bit. So it looks like, okay, now you never cross this x equals 0 line. This graph has what's called a vertical asymptote at x equals 0. So you get very close to 0, but you don't ever actually get all the way there. Now on Desmos, it will eventually say 0. That's because Desmos rounds its numbers. But really, you're at 0.000007 or something like that. Now your graph here, it does keep going up, but not, excuse me, not very fast. Now, even though it looks like maybe the graph is starting to go flat, it really is going to continue going up forever. So if we take, for example, our x's and make them go to very, very high, let's go up to 1,000. Notice your graph's not going up very fast, but it is going up the whole time. That's going to continue on and on forever. If we go up to like 10,000, the graph continues going up forever and ever, just very slowly. So there we go. That's what the inverse looks like. So a rough sketch of it. Here's the important properties. For the graph of your inverse, you want to have it kind of go up and then kind of like that to the side. So keep going up, but not very fast, and make sure that you don't ever cross this line at x equals 0. All right, next up. If the input for the inverse is 81, what is the output? Okay, let's think about that for a moment. If the input for the inverse is 81, what is the output? So we're essentially saying, let's take this table. That's not what we want. Let's take this. That's not what we want. Let's take this table and add another entry. Let's put 81. And just for color consistency, I'm going to switch back to my blue. Let's put 81 over here. What then would we end up with on this other side? A couple of ways to get there. One of the easiest is we got a graph made already. Let's just see what it is. So if we put an x value of 81, I'm going to go back here to a regular zoom. Now, in order to see where x equals 81, we've got to make our x maximum something bigger than 81. All right, so right here on the inverse graph, it says when x is 81, I'm going to look at the intersection to find the output. The output is 4. Okay, let's see if that makes sense. So we've answered the question. On the inverse function, when 81 goes in, 4 comes out. Why is that? To do that, let's think about this. That would mean that on this original function graph, if you put a 4 in, an 81 comes out. So 4, 3 to the 4th power, that's 3 times 3, which is 9, times 3 again, which is 27, times 3 again, which is 81. That's why this is happening. So really, here we start with exponents and see what the end result is. Here, the exponents are what the output is. On the inverse function, we're being given the exponents to put on 3 to get the numbers we started with. So what exponent do you put on 3 to get 9? Use an exponent of 2. What exponent do you put on 3 to get 81? Use an exponent of 4. So we know we ended up with 4. And why does that happen? It's because this inverse function is telling me what exponent on 3 will get me this number I started with. So using these answers, if you put a number for x in the inverse, how can you describe the output? Not the most straightforward question, but it comes down to this. When a number goes in, the output, the y value, gives us an exponent. Specifically, it gives us the exponent that we need to put on 3 to get the number that we started with. We'll summarize that idea in the next part of the lesson.